This is a solubility equilibria study on video that is suitable for AP Unit 7. I just show you here a big part of Natural Bridge Caverns, an underground lake, which shows this is a void in the limestone. The limestone has actually been dissolved by carbonic acid, and we believe that limestone caves are almost always formed in this way. Precipitation is the formation of a solid from a solution. It is the reverse of the process of dissolution. Dissolution is the process by which a substance dissolves and is the reverse of precipitation. When you dissolve a salt, calcium carbonate is a salt. When you dissolve a salt, there's two things that have to happen. You have to, the endothermic process of pulling the anion and cation apart, calcium ion from the carbonate ion, and then the exothermic surrounding of the water, solvating the ions, which of course is what actually creates the water solution, and the ions then are separated from each other by a bunch of water molecules. Now the importance is that selective precipitation is used in industrial purification, especially when you want crystals. You want to prevent the formation of scales on boilers and teeth. And kidney stones are similar things in your body. And then for precipitation forming minerals that you can mine, and dissolution will remove those. Saturation. A saturated solution is a dynamic situation. That is, the dissolving and the precipitation are going on at the same time, but the rate of dissolution is equal to the rate of precipitation. In an unsaturated solution, you don't have enough dissolved solid to cause precipitation, so there is not an equilibrium situation there. Essentially, you've got a saturated solution when you've got crystals at the bottom of the closed container and the solution right above it, and the crystals at the bottom are not visibly dissolving into the solution. And then you have a high energy situation, which is unstable, called a supersaturated solution, and you've got actually more quantity of solute in the water, surrounded by water molecules, than the temperature warrants. No solid is present. If you make solid present, the supersaturated solution will attain a low energy state and the excess solid will come out. Solubility is the greatest amount of substance that will dissolve in an equilibrium, make a saturated solution, in a given volume of solvent at a particular temperature. We're almost always talking about water solutions. For example, silver chloride will dissolve in water, but not very well. At 25 degrees, you can get 1.8 milligrams in a liter, 1.3 times 10 to the negative fifth molar. That's very, very little. Now, most, but not all, solid solubilities will increase as the temperature increases. This is a solubility curve graph. It has a number of salts, potassium iodide, sodium nitrate, potassium nitrate, ammonium chloride, and so forth. But it also has some gases like hydrogen chloride, making hydrochloric acid, ammonia gas, making ammonium hydroxide. And as you can see, most of the salts increase with temperature. In fact, what you see here, except for sodium sulfate, all of them are dissolving more in hot water than in cold. Sodium chloride has an almost flat solubility curve. You must know how to read these curves to determine at any given point how much solute will be in a saturated solution, because this is the saturated solution line. So, what's the solubility of sodium nitrate at 30 degrees? All right, we go here to the 30-degree temperature, and we look for the sodium nitrate line, and there it is, and you can read it if you wish. Also, questions, and you see that if 100 grams of water is saturated with potassium nitrate at 70 degrees and cooled to 20 degrees, how much salt will precipitate? Well, you go here to the 70-degree line, you come up to the potassium nitrate line, which is just a little higher than sodium nitrate, and you read that off. And let's just say 140, it's close. And then if you chill it to 20 degrees, what does it have in it? Well, potassium nitrate, about 32, 33 grams. So you subtract the 140 minus the 32, 33, and you get your answer of how much will precipitate. So be familiar with that. It's the kind of question you can ask. Now, I'm just going to give you these definitions. I don't want you to memorize them, but it gives you an idea of what we determine as soluble ionic material versus insoluble or slightly soluble. It's kind of a sensible way of seeing it. If you can put less than 0.1 grams in a liter, then we call it insoluble, even though it is very slightly soluble. Most salts dissolve into ions when they dissolve. Equilibrium then is established between the solid salt and its solvated ions. Here's an example. Lead sulfate solid is in equilibrium with lead ions, lead 2, and with the sulfate ion. You can describe it by what we call a mass action expression or equilibrium expression. Mathematically, this is K. This is the same K you see in the rest of Unit 7, but it's called a solubility product, K, because you have a dissolved substance here, a dissolved substance here, and they're in equilibrium with a solid. Solids are not attributed a concentration. So you're thinking, well, I'll divide by the concentration of the lead sulfate solid, but there is no concentration. So there's nothing to divide by. That's why you have only these terms. This makes solubility a pretty easy thing to determine the mathematics of. Reactants and products in condensed phases are not in the equilibrium expression, so they don't show up in the mass action expression. Now, one may provide solubility information in two ways. First, you can give the solubility, and that's usually in grams of solute per 100 grams of solvent. You can also show the solubility product, the KSP, because the two properties stem from the same phenomenon, and so they refer really to the same process. Now let's remember Coulombic attraction from our first semester. Forces of plus to plus or minus to minus repulsion are called Coulombic repulsive forces. Forces of plus to minus attraction are called Coulombic attractive forces. And they're going to vary, and they're going to vary strongly inversely as distance changes. So the closer they are, the higher the force. Coulombic attraction. Solids that dissolve in water are held together by Coulombic forces that are too small to offset the kinetic energy of the water molecules around them. So, when, for instance, potassium nitrate is stirred into water, the water immediately is attracted. Notice the negative end of the water is attracted to the positive, the cation, and the positive end, the hydrogen end of the water, is attracted to the anion. In some cases, the tests have asked you to draw these. You must draw them like this, with the water molecules oriented properly in their dipole to attract the anion or cation. If you've got a solid that doesn't dissolve in water, those Coulombic forces between the anions and cations are too strong for the kinetic energy of the water molecules around them to knock them apart. And so we have a situation like this, where there is attraction, but the crystal stays together because the lowest energy state is in fact in the crystal. So here's a kind of problem you may see. What's the KSP of lead iodate, lead 2 iodate, if 0.00896 grams will dissolve in 400 milliliters at a certain temperature? Well, let me show you how to do these problems, because KSPs are important. The molarity of all ions must be calculated in the saturated solution, because that's what we're talking about. And then you have to plug it into the equilibrium expression, the mass action expression, and solve for the product. So here we go. The molar mass of lead iodate is 557 milligrams per millimole. So we're going to divide that into 8.96 milligrams, and we get concentration of 4.02 times 10 to the negative 5th molar when we get the number of moles of the lead iodate from here, and then we divide by 400 milliliters. Remember, it's millimoles per milliliter, and we end up with a 4.02 times 10 to the negative 5th molarity. Now, what is that of? Well, it's the molarity of the lead ions, because it's the molarity of the lead iodate, and there's only one lead in every lead iodate. Now, what is the molarity of the iodate when you have this 1:2 relationship? And I think you can see it's going to be twice 4.02 times 10 to the negative 5th. So we're going to first, watch it, this is important. We first double it to give you the molarity itself, but then the mass action expression, you have to square the iodate 2. So yes, the 2 shows up twice. Once to give you the correct molarity of the ion, and then also you put the superscript 2 on it because you have to exponentiate that. Now, when you multiply then these together, so this is about 64 and this is 10 to the negative 10th. When you multiply these two terms together, you get 259 times 10 to the negative 15th. Now, I encourage you to do that yourself, or 2.59 times 10 to the negative 13th. And remember, this is an equilibrium constant, so you don't fool with units. Here's one for you to do, and I turn the video off. Just pause it and do this one, and then check your answer. And it says the Rice tables. So try this, and then we'll get started again. So if you looked at the stoichiometry here, the copper iodate breaks up into 1 copper and 2 iodates, and you're given the mass action product there. Let's see how to do this. Stoichiometry. Here's the mass action expression. The iodate is twice times the copper, so you're solving for the copper. So the KSP is the copper times 2 times the copper squared. So you have the equation 4 times the cube of the copper, and when you divide this out and take the square root, there you go. The copper is 3.3 times 10 to the negative 3rd molar.